Here we have our RFT-03C Amitec Electronics Butler crystal oscillator RF module. Here a crystal is being used in its overtone mode, and the roughly 5th resonant frequency of the crystal oscillator is being used to generate the frequency. We connected the crystal in the feedback path of a transistor circuit, and the output of the oscillator is being monitored on the spectrum analyzer. We are using 2 coils in this Butler crystal oscillator. One of the coil, which is in parallel to the crystal, is used to suppress the fundamental mode of the crystal oscillator. The other coil, in function with its L1 and C6 components, forms a tuned circuit which tunes at a frequency roughly approximation closely to the overtone frequency of the crystal. We change the L1 resonant frequency to bring the tuned frequency near to the overtone frequency, and the moment we are closer to the crystal overtone frequency, the oscillator pulls into the crystal frequency, and the same is being generated with the Butler crystal oscillator. So we are able to use higher frequencies for the crystal oscillators. Normally crystals are not available in the fundamental mode for more than about 20 MHz. If we have to use the crystal at a higher frequency, we have to use overtone modes for the crystal, and we have to use Butler crystal oscillator in that case. As you can see, the fundamental frequency of this particular Butler oscillator right now is roughly about 88 MHz. The power generated is roughly about 0 dBm. The second harmonic is at a level of about -12 dBm, and the second harmonic is at a level of -22 dBm. So we can measure the level of the fundamental, and we can measure the frequencies of the various harmonics, and we can measure the frequency pushing characteristics of the Butler crystal oscillator by changing its supply voltage. Right now the supply voltage is roughly about 20 volts. If I reduce this supply voltage, I observe that the level of the harmonic goes down, while there is a frequency at which the oscillator shifts into its frequency and it stops functioning. This is because of the pushing characteristic. The tuned frequency of the resonant circuit has shifted from its crystal frequency, and that is why we see such waveforms. Now we see that the oscillator dies down. If we again increase the frequency, the oscillator comes back into its overtone mode. It tries to push to cross the resonant frequency of the crystal, and now it locks into the center frequency of the crystal, and we have a stable output of the Butler crystal oscillator.